Hi guys, good morning. Welcome back to the next lecture. In this, we're going to see remove max number of edges to keep the graph fully traversal. Firstly, if you have watched the last video, yesterday's videos, I highly recommend you can code this easily. If in worst case you have not got the logic, I still recommend, if even at the mid of this you get the logic, just pause the video, no matter watch time, no matter nothing, just pause the video or don't watch it, but code by yourself, because you can code by yourself. Yesterday I told you exact same thing too. But yeah, before further ado, let's start with the problem. It says that Alice and Bob, there are two people and have an undirected graph of n nodes and 3 types of edges. Cool. We have n nodes and 3 types of edges. How is the type like? The type 1 is that it can be traversed by Alice only, which is of red color they have shown. Type 2 is that they can traverse by Bob only. Type 3 is they can traverse by both Alice and Bob. Given the array edges, where edges of I is something like this, where edge represents first is its type, if it of 0, 1 or 2, sorry, 1, 2 or 1, 2 or 3. Next is if it connects what two vertices, U and V, represents the bidirectional edge of type this of from between node UI and VI. Find the maximum number of edges you can remove. Maximum number of edges you can remove, so that after removing the edges, the graph still be fully traversal. You have to remove the maximum number of edges. Thus, you will try to make sure that you use minimum number of edges, because you have to remove the maximum number of edges. So use minimum number of edges. That's the reason. What we will do is, the graph can still be fully traversal. The graph is fully traversal by Alice and Bob if starting. Okay, how does a minimum spanning tree or a tree is worked? Like, we just have to make a tree out of this graph that at least I can visit every node from every other node, and in a tree you can visit every node from every other node. It is the minimum thing which you have to do. Cool. Return the maximum number of edges you can remove, which means you have to choose minimum number of edges to build your graph or tree, because ultimately it's a tree, because ultimately you have to just connect all the edges of for Alice, all the nodes for Alice, all the nodes for Bob. That's the reason it will be ultimately a tree. Or return -1 if it is not even possible. Let's look at the examples itself. Firstly, if you just clearly look, then we have the graph right here where the red indicates Alice, which Alice can use, green indicates which Bob can use, and blue indicates which Alice and Bob both can use. So basically, I have these 1, 2, 3, 4, 5, 6 edges, right? I want to remove maximum number of edges, right? I want to remove. So I will try to take minimum number of edges, which means out of this graph, I will try to take, out of 6 edges, I will try to take minimum number of edges that I can build the graph or tree, I should say, for both Alice and Bob. It is for Alice, it is for Bob. Now you will say, Aryan, okay, that makes sense, but how to actually know that which edge to pick? I have 6 edges and I have to make a graph / tree, because I just wanted to correct all the nodes. So which edge to take? I'll say which edge has the maximum impact. You will see this blue edge right here, this one edge, it can connect both for Alice and for Bob. This one edge connected 1, 2 for also Alice, also for Bob, while this green edge right here, which connects 3 and 4, it is only connecting Bob, right? This red edge right here, it is only connecting, sorry, this red edge right here, it's only connecting 2 and 4. Thus, one thing you for sure know, I will take for sure the type 3 edge, which is actually a blue edge. See, blue is type 3. I will take the type 3 edge, which is a blue edge, because firstly I will just grab this blue edge because it has the maximum impact. How? I will be able to actually connect both for Alice and as well as for Bob by this one edge. One edge has 2 impacts. So I will just try firstly I will just try to to grab this type 3 edge because it is connecting the component for both Alice and for Bob. Cool. That thing, Okay, if I just grab this edge, then after that, what should I grab? You can grab anything after that. You can grab maybe this green edge or maybe this red edge, anything after that. But firstly, try to grab blue edge. Oh, when we say we grab an edge, what we are doing? We are actually grabbing an edge and building a graph or a tree out of it. Oh, as the edge is added, firstly, how to know the edge is being added or not? Which means, let's take this example again, where now I'm pretty sure of one thing, that I will take firstly the type 3 edge, which is a blue edge, which is for both Alice and Bob. Then I can take any of them, either for Bob only or either for Alice only. So one option is we can just sort it to actually get the 3 ones at the beginning itself. But it is not required to sort, mark my words. It is just to make your code shorter, but it will increase the complexity. But still, you can just, my main aim is to just iterate on the edge which is of type 3, which is can be used by both Bob and Alice. You can just go and iterate on this entire edge list and just firstly grab this edge 3 types, and when it is done, then you can go on to the remaining types. Or you can just sort it. It will increase the complexity by log times, but still, that is you can do. I showed you 2 options, but ultimately keep one thing in mind. What is your aim? I just grab these edges. Cool. As soon as I grab the first edge, I'll ask, hey, is there an edge between 1 and 2 for Alice? So it's not required to have an edge, right? It's just okay, it should be connected. Firstly, initially the graph looked like this: 1, 2, 3, 4, all are disconnected. Now I will ask, shall I add this edge for my Bob? But for adding the edge, I should make sure that okay, both are in different components. Only then it is actually good to add an edge. Else it is not good. Else it is why it is required. If it is already building a graph, then why it is required? If it is not, then I will just find, okay, is that 1 and 2 already connected? We find that. If it is not, then we just build the graph. We connect 1 and 2 for both Alice and Bob. Cool. Now you saw what happened. We found if this edge is actually impacting, which means if I will just find, is this 1 and 2 in the same connected component, No. So I will just make a graph out of it, which means I will just connect them, which is actually building the graph. Ultimately connecting them, building the graph, connecting, union them. Thus we connect 2 components which are just doing the union, as you saw in the last video also. How we are building a graph is nothing but union. How we are finding if they are actually already connected in the same connected component or not, it is just finding. Simply you know one thing: to apply this operation of finding if they are in the same component or just bringing them in the same component by applying an edge, you can just apply a union find and do this operation. But now let's see what is the operation we have to do. So one thing we ought to know, that if they are, and in the last video also many folks were saying that what is the use of this union, what is the use of this bool in our union function. So basically it will just return you that was the union actually required or not. You can add a union between 1 and 2, but maybe it has already connected. If it is already connected, it will return a false. But if you are connecting them right now, so it will just connect that and return a true. By this return statement, you can get to know if it is already connected or you are connecting that. So if it is not connected already, which means it is returning true, which means I have actually connected it now, then I will connect that same edge for both Bob and Alice. And also if 1 edge is added for them, both are happy, both have increased their 1 edges. So Alice and Bob edges are increased. Else if maybe both are in the same component, 1 and 2, I don't have to add that edge. What I will do is I'll just remove that edge. Now, okay, first edge was done. The graph looks something like this by adding this edge. Now, next edge comes. It is adding 2 and 3. Are 2 and 3 in the same component? Which means, are they connected anyhow? 2 was different. Like what happened was in the last step, it was something like this. It is not connected. So 2 and 3 are not connected. No worries, just add that, just connect that. Same as we did above. Cool. Then the next edge comes. Now it's a green edge, which means it can only impact my Bob. I will just say, hey, Bob, for you 3 and 4 are connected. 3 and 4. He will say, no, they're not. I will just find, it will say, okay, they are in different components. No worries, Bob, you can use this edge. Cool. Bob will use this edge right here to actually connect it. So you will see if that is in different components, which means by doing union, it is actually impacting, it's returning true. Then I can just increase one edge of Bob because Bob has got one edge. Else, if it is not required for Bob to add that edge, if they are already in the same component, then I can just return, okay, just remove that edge, it's not required. Now, next comes, is it required to add an edge between 1 and 3? Which means if I just add 1 and 3, but I can already see it is already in the one component. My union will return a false because even after applying a union, I'll still say it is already the same component. So why to do a union? So why to apply this edge if they're already the same component? So I will not use this edge, which means I will add 1 in my removed edges because it is an edge which was not required, and I'm going greedily. I'm thinking, okay, firstly I will just grab, oh, what is the edge which can impact both of them. Then okay, when it is done, then I'll just check, okay, Bob has all these edges remaining, Alice has all these edges remaining. Let's go, let's try, okay, if Bob is having any fun or any benefit with adding that edge, if Alice is having any benefit by adding that edge. By adding this edge between 1 and 3, Alice is not having any benefit because graph is already connected, 1, 2, 3 already connected. So I will just remove this edge. Now increase my removed edge. Now move on to the next edge, which is between 2 and 4. Earlier 2 and 4, oh, they are in different components. So adding this edge will actually help Alice. So I will just add this edge between Alice and between 2 and 4, which will actually use this particular edge for Alice. Cool. Now going to the last edge. What will happen is 1 and 2. 1 and 2. They are already in the same component. So why do I add this edge? Just remove this edge. So I add this edge in my removed edges because ultimately I need to return the maximum number of edges I can remove such that I can build the graph kind of a tree for both Alice and Bob. And that is how what we did. Lastly, we need to make sure that both Alice and Bob are completely reachable. Like every node is reachable from every other node, which means a tree is at least built for both of them. And why at least? It is because it will at least be and exactly be. Why? Because we want maximum of edges to remove. If in worst case we build a graph something like this, let's imagine. So we can for sure remove this one edge, right? Thus, I will just try to remove as many edges. So ultimately, I will just land back to a tree only to actually get the maximum of edges removed. Now, if it is done, if both Alice and Bob are actually a tree, we are very happy. I can just say, okay, it is the removed number of edges which you can remove from this entire graph thing, this thing. But if it is not the case, if maybe Alice and Bob are not done, maybe anyone is remaining, I have to return -1 because it is said, okay, it is not possible. Let's look at the next examples. For this, you can see, firstly, you will try with the blue ones, which is of type 3. You just add it, use. Then you will just go on to this particular edge between, like red edge for Alice, 1 and 4, connected, not connected. So add this edge between Alice, then you go on to the green edge for Bob. Is it connected 1 and 4? No, not connected. So added. So basically you used all the edges. No edges were removed. So 0 removed edges. In this example, firstly I will just add this edge between 2 and 3 for both Alice and Bob. Then I just go on for Alice. Use this 1 and 2 different. So just add this edge. 3 and 4 different. So just add this edge. Now all the edges are consumed, but still I can see that my graph is not connected. The number of edges right now should have been n-1, but it is nothing but 2. It should have been 3. So for sure the graph is not connected. Thus I need to return a -1 as we saw above. That is all what we have to do. It's pretty simple. I hope that you guys got it. Let's look at the code. The standard Bob template for DSU, which is the best for, because the complexity of path compression and union find, union by rank or union by size is actually minimum. So as I have showed you also in the last lecture, the exact same template for the DSU. Still, I'll just go on through it. That firstly, what we do is initialization. Then we have this find function, which actually go on and find what is the parent, and also parallelly keep on assigning the parent, which is path compression. It just compresses the path itself. If you have not watched the last video or basically the DSUs, I highly recommend that. The problem name was, I will just quickly let you know what was the problem name. It was checking the existence of edge length limit paths. 1697 Leetcode problem. So just search on YouTube checking existence of edge length limited paths by Aryan Mittal, and you will just find that video. In that video, I've explained very deeply about everything of this DSU, how this implemented, all that stuff. But if you have already known that, just go and see that, okay, it is just path compression. It is just assigning the path and also compressing the path, which means making the tree flattened. And apart from that, it is just union. Union is nothing but if a small root, then I just assign it to the bigger parent, like whosoever is bigger. If A and B, if I have X and Y, it is two subtrees, then I will just keep on assigning maybe Y to X or X to Y. And that is the union operation for a unifying find operation and a DSU. Don't worry, the entire notes is down below itself. Now comes the interesting part. Here we just sorted it. The only reason to sort was to get the type 3, to evaluate the type 3 first. But I am saying it is not required. You can improve the complexity to O of E only by just iterate on this entire list once and evaluate only the type 3 ones. When it is done, now iterate the entire edge list again, and now what is not of type 3, which means it is of 1 or 2. Now evaluate those types. But just make sure that you maintain order. First 3 and then 1 or 2. That's it. You can sort it, you cannot. Sorting it will increase the complexity. I highly don't recommend it. But it is that your code will look shorter. That's the reason I just did it like this. Cool. Now we initialize the graph for both. It is just initializing our union find for both Alice and Bob. Now comes the interesting part. Removed edges, which actually I can remove. Alice edges, which Alice is using or Alice has used. Bob edges, which Bob is using or Bob has used. Now I will just iterate on all the edges for sure. Firstly, I will check for of type edge as 3, as I said. Firstly, I will evaluate for type 3. Then I can evaluate for 2 or 1. Like I can have it in any order. You can have it in any order. But firstly, you have to evaluate of type 3 only. Now comes the interesting part. I will just check. Is adding an edge between 1 and 2, between U and V, between U and V, is it actually connecting some component? Is it actually helping us? If it is, then just connect it. Okay. And just do a union of those two vertices, U and V, and I'm good. But if I'm just connecting an edge between U and V for Alice, I can also do the same for Bob also, because Bob also can use of type 3. So I'll just use that for Bob also. And as both have connected 1 edges, so I'll just increase the edges for both of them. If in other case, if I have not connected an edge between U and V, then just remove that edge, which means not required. Remove the removed edge. Cool. In the next iteration, what if this edge of type 3 is finished? Now comes the edge of type 2. So I will just, okay, it can only impact Bob. So just ask Bob, is it impacting you? Adding this edge, unioning this edge is impacting you. He's saying, yeah, I did a union and it was impacting me. So no worries, Bob, you can have this edge. If it is not impacting you, if it is false, then I can just return, okay, Bob, leave it. Just add it in the removed edge. Same goes for Alice. Is Alice, this edge between U and V, is it impacting you? Yes, it is. Add in the edge of for Alice. Else add in the removed edges. At last, as I showed you also, that I will check it is actually making a tree for both Bob and Alice? If it is yes, then I'll just return the removed number of edges which I have computed so far as I was going on. Else I can just return a -1. That is it. The time complexity right now for this code written down here is O of E log E, but it is not the best complexity. You can easily, very easily, just the code will look a bit longer because you have to do 2 for loops, one and after that again, but it is actually like this. You can actually achieve by just iterating on this list again and evaluate firstly for type 3. Then at the next step, you can just say, okay, whatsoever is not of type 3, which means ultimately it will be of 1 or 2, then you can just iterate on those. Time complexity will ultimately reach to O of E, but right now it is O of E log E. Space is O of E because of DSU. It needs parent, it needs rank, that of array. Complexity, why a DSU can do operations in O of 1, I have actually explained in the last video also, checking existence of edge length limited paths very briefly. So basically it's inverse Ackermann function, which is actually, it can go up to maximum of O of 5 steps. It's at max for any number whatsoever. And here you can see for this sorting, it is O of E log E. I have said it is not required at all. You can actually do the by just simply iterating on the edge list again and again. Now I just iterate on my edge list. I just checked. Iterating on the edge list is nothing but O of E. Union operation is nothing but O of 1 operation. Find operation is also nothing but O of 1 operation. It's actually O of 5, but it's actually a constant, so it is O of 1 only. Thus, and yeah, all this I have explained in the last video only. Video name I told you. Checking existence of edge length limited paths by Aryan Mittal. Leetcode 1697. Now ultimately the same code, same complexity. That's the reason we have the complexity of O of E and O of E log E for time, but it is O of E. It can be reachable. That is all code for C++, Java and Python. If you have not marked the code for DSU as snippet, I don't know what you are doing. Just mark it right now and here. And I hope that you guys got the intuition properly. And yes, you guys are going to learn. Goodbye. Take care.